All right, so we're going to start off with a little introduction here. So many of the fundamental results that we've derived for planar rigid body kinetics still hold for 3D motion. For example, the motion of a rigid body relative to an inertial frame is still going to be defined by Newton's laws. We'll have the sum of the forces is equal to the mass times the acceleration of that rigid body. And then the sum of the moments about the center of mass will be equal to, in this case, we're going to write it as the rate of change of the angular momentum about that position, center of mass C, because that angular momentum is going to change compared to what we saw for 2D planar kinetics. We can also compute angular momentum with respect to some other point O, that is fixed in an inertial frame. In that case, we would write that the sum of the moments about that point O is equal to the rate of change of the angular momentum about that point, or h dot sub O. So equation 1 here is applicable to any system. And in 3D motion, there are now 3 equations rather than just 2. Equations 2 and 3 are applicable in particular cases. To be honest with you, I'm not sure why I didn't say that. I think they're applicable everywhere as well. I'm not sure why I didn't put that. I can't think of a case where it's not true. However, there may be cases where it's not true. I don't know. I mean, to me, it seems like a fundamental law. But anyway, certainly equation 1 is applicable everywhere to any system. All right, so just in planar motion, the center of mass is going to be able to move independently from changes in the orientation of the rigid body, meaning that if we are computing the motion using the center of mass, we can separate any kind of angular changes or any kind of angular velocities. We can separate those from the motion of the center of mass. All right, so there is a natural extension from 2D to 3D for equation 1. You just add an additional equation for the third direction. This is not the case for equations 2 or 3. We will find that we cannot just write the angular change of angular momentum as a sum of 3 terms like you can for the acceleration. And we'll end up going through and finding what's known as the inertia tensor to deal with this. All right, we're going to go through angular momentum. And then after we do angular momentum, we'll end up with what is known as the inertia tensor. And then we'll go do impulse and momentum. All right, so we're going to consider a rigid body, which we'll label as B. A rigid body is over here. It has a set of body axes, X, Y, and Z, and it lives in a reference frame O. Reference frame is shown down here, with inertial axes, capital X, capital Y, capital Z. As drawn, these 2 axes are kind of in the same direction, but this doesn't have to be true because the rigid body B can rotate and move. And then as it rotates, the axes, lowercase x, y, z, those are going to rotate with the rigid body. So that are fixed to the rigid body and they move with that rigid body. Our rigid body has a center of mass, and that's where we're fixing our body axes. And we're going to consider some infinitesimal point, we'll say pi, which will have a mass of dm, or we could also use delta mi. We're going to kind of use both discrete points and then also continuous or infinitesimal points in integrals as well throughout this. So our rigid body is going to have an angular velocity of omega, and we're going to project this onto the Cartesian system at point O. That's going to give us that omega is equal to some omega x in the I hat direction plus an omega y in the j hat direction plus an omega z in the k hat direction. We're going to draw a position vector from our origin to our center of mass. We'll call this R sub C. Draw a relative position vector from C to PI. We'll call that R sub I, and we'll write that down in a moment. At point I, there is some velocity, which we'll call V sub I. And the rigid body has some angular velocity, omega, which we just projected onto our inertial frame, or our inertial axes. All right, we're going to express the position vector or relative position vector of our particle, Ri. We're going to say that this is equal to xi plus yj plus zk. And we're also going to say that this is just equal to r without the I as well. All right, so our angular momentum of the rigid body is going to be h sub c, so we're looking at the center of mass. This is going to be the summation from I equals 1 up to n particles of the quantity r sub I crossed with v sub I times delta m sub I. Or we can write this as an integral, and we're going to integrate over our body of r crossed with omega cross r times dm. So we're doing an integral with respect to the mass of the system, or the relative volume integral with respect to mass. Oh, I'm sorry. Hold on. I got ahead of myself. Let me correct this. This should actually, at this stage, just be R crossed with V dm. In the next step, we're going to plug in we're going to use a two-point formula for VI, and then we're going to expand that, and then we'll substitute in, and we'll see where this takes us. Okay, so we know that V sub I is equal to the velocity of the center of mass plus omega crossed with R sub I, or just R if we want. And then our angular momentum H sub C will become the summation from I equals 1 to N of R sub I crossed with omega crossed with R sub I, all of that times delta mi, which is equal to the integral over the body of R crossed with omega crossed with R dm. All right, we're going to use equations 4 and 5 on the previous page. Those are where we projected the angular velocity into our inertial frame, and we projected the position vector, relative position vector, into the inertial frame. We're going to use those and the identity I put up there. And doing that, we're going to end up with the following, which is going to be a very long equation. So h sub c is going to be equal to, we're going to have 3 components in each direction, so we're going to end up with 9 different components. We're going to have omega x times the integral of y squared plus z squared dm minus omega y times the integral xy dm minus omega z times the integral of xz dm. All of that is in the I direction. In our j direction, we're going to get plus, we're going to get minus omega x times the integral of xy dm plus omega y times the integral of the quantity x squared plus z squared dm minus omega z times the integral yz dm. That's in our j hat direction. And then lastly, in the k hat direction, we'll have minus omega x times the integral xz dm minus omega sub y times the integral of yz dm plus omega z times the integral of the quantity x squared plus y squared dm. All that in our k hat direction. Okay, I just want to go up and make one correction to our diagram. We're going to add in the unit vectors. We have I hat in our capital X direction, k hat in capital Z direction, and j hat in the capital Y direction, which is our standard Cartesian. Should be no surprise. I just wanted to add it there. All right, so the integrals containing the squared coordinates are what we call the centroidal mass moments of inertia about this axis xyz, and that is, we will call them I sub xx is equal to our integral of the quantity y squared plus z squared dm. I sub yy is equal to the integral of x squared plus z squared dm, and then I sub zz is going to be equal to the integral of y squared, or actually x squared plus y squared dm. All right, and then the integrals containing products of coordinates, we call these the centroidal mass products of inertia. And we'll write those as I xy is equal to the integral of x times y dm, I sub yz. This is equal to the integral of y times z dm, and then I sub xz is equal to the integral of xz dm. Our angular momentum then can be written as h sub c is equal to quantity I sub xx times omega x minus I sub xy times omega y minus I sub xz times omega z. That's in our I hat direction, plus quantity minus Ixy omega x plus I sub yy omega y minus I sub xz. Oops, that should be yz. I sub yz times omega z. That's in our j hat direction, plus minus I sub xz times omega x minus I sub yz times omega y, and then plus I sub zz times omega z in the k hat direction. And then we can rewrite this as our angular momentum h sub c is equal to the tensor I, the double underline, multiplied by our angular velocity vector omega, where I under double under bar is the inertia tensor, which is like a higher dimensional vector effectively. It's not necessarily a matrix because it changes with time. And it can change with orientation, and it has really special properties about it that typical, like a general matrix, won't have. And our inertia tensor here is then defined as being equal to, we're going to represent it as a matrix, I sub xx minus I xy minus I xz minus I xy, I yy, then minus I yz, and then lastly we'll have minus xz minus I yz, and then I z z. So in general, omega and h sub c are not in the same direction. However, for some given omega, the angular momentum is going to be same regardless of what coordinate system we choose. The inertia tensor depends on the coordinate system we choose. And as a result, we can actually always choose a special set of body axes, x prime, y prime, and z prime, such that our inertia tensor becomes diagonal, or I double underline is equal to I sub x prime, and then 0, 0, 0, 0, I sub y prime, put another 0 there and a 0 there, and then I sub z prime. And in this case, these axes are called the principal axes of inertia, and the diagonal terms of the tensor are called the principal centroidal moments of inertia. So the angular momentum and the angular velocity are only going to be in the same direction if the angular velocity is directed along one of these principal axes of inertia. And in that case, we'll find that h sub c is simply equal to I sub x prime times omega x prime times our I hat prime. This prime, in all these primes indicating that we're along the principal axes of inertia, plus Iy prime omega sub y prime j hat prime plus I sub z prime omega sub z prime times k hat prime. All right, we're now going to talk about the angular momentum of a rigid body with respect to some other point other than the center of mass. This is going to be a combination of the linear momentum and the angular momentum of that rigid body. So we're going to draw our little diagram here. We have our reference frame O with a fixed point O. Our position of our center of mass is going to be R sub C. We're going to have some linear momentum L. This will be equal to the mass times the velocity of the center of mass. Then we'll also have some angular momentum, which we'll write just as h sub c. And then our angular momentum about the point O is going to be h sub O is equal to R sub C crossed with the linear momentum, or the mass times the velocity of the center of mass, plus the angular velocity about the center of mass. So if the rigid body is constrained to rotate about some fixed point, then in general we're going to want to use our equations 12 and 13, but we're going to compute everything about that fixed point rather than the center of mass. So that's a higher extension of what we did when we did parallel axis theorem. All right, with that we're going to move on to take a look at impulse momentum. We'll then look at work and energy, and then after that we'll be on our way to look at equations of motion. Okay, so in general, the principle of impulse momentum stays the same. The only change is the angular momentum, which we've already derived what that angular momentum looks like. And as a result of that, thus, we can write that the linear momentum at time t equals 1 is L sub 1 plus the impulse, or the integral from t1 to t2, applied to the summation of all of the forces acting on the system times dt, which is then equal to the linear momentum at time t equals t2. We're going to get the same type of equation for the angular momentum. We'll get h sub c1 plus the integral from t1 to t2 times the summation of all of the moments about the center of mass at time t equals 1 dt is then equal to the angular momentum at time t equals 2 t2. So impulse momentum is exactly what we've done before. We just have a more complicated angular momentum now. And there are also 6 equations to deal with instead of 4. Or I think we had 3 before. We now have 6 equations to deal with. There's an additional linear momentum term in the third direction. and there are two additional angular equations, because we now have to deal with two additional directions. But everything we've done before now still applies. Same thing with impacts. If we want to deal with impacts, we can now consider impacts in 3 dimensions. All right, we're going to go on to work in energy. So the kinetic energy in this case, considering again an infinitesimal point dm, we can express our kinetic energy as T is equal to 1/2 times the integral of V dotted with V dm, so integrating over all of the mass, where V is the time derivative of the position vector from O to our mass element dm. And in this section, we're going to compute all of our derivatives in the reference frame O. So in our inertial frame O. We're going to then relate our velocity v to the velocity of the center of mass, and we'll get here simply that v is equal to vc plus omega crossed with r. Where r here is the relative position of dm with respect to the center of mass. We'll then find that the kinetic energy is going to equal 1/2 times the velocity of the center of mass dotted with itself times the integral over the body dm plus 1/2 times the integral over the body of omega crossed with r dotted with itself, so omega cross r dm plus Vc dotted with the quantity omega crossed with the integral over the body of r dm. And this last term goes to 0 because there is, for every r, there is an equal r in the opposite direction, equal in magnitude but opposite direction, that will cancel it out, such that this integral right here, because the integral over the body of r dm equals 0, so this quantity here is 0 because that integral goes to 0. We'll then use the following identity shown there, and then we can write that our kinetic energy here, T is equal to 1/2 integral over the body of dm, that is just the total mass of the system, so 1/2 m times the velocity of the center of mass dotted with itself plus 1/2 omega dotted with the integral over the body of the quantity r crossed with the quantity omega crossed with r, and then all of that times dm. All right, so the remaining integral is actually just the angular momentum of the system, and so thus we can write here that T is equal to 1/2 m Vc dotted with itself plus 1/2 omega dotted with h sub c, or in the final form we'll write this as T is equal to 1/2 m Vc dotted with itself plus 1/2 omega dotted with I double underbar omega. means it's a tensor, which is a higher order vector. So in this case, it's a 2D, a two-dimensional tensor. But tensors can be n-dimensional. And like continuum mechanics, when you're thinking about deformation, you end up with fourth order tensors that relate stress to strain, for example. The double underbar means here it's a tensor. Specifically, it's a second order tensor. All right, we can also expand this into components. And we'll get this lovely expression where t is equal to 1/2 m times v cx squared plus v cy squared plus v cz squared plus, so that one is probably relatively straightforward and what you would expect. The next one is going to include a bunch of extra things that you wouldn't necessarily expect. So we're going to have ixx times omega x sub x squared plus I sub yy times omega y squared plus I sub zz times omega z squared, and then minus 2 I sub xy times omega y omega x minus 2I sub yz times omega y times omega z, and then minus 2I sub xz times omega x times omega z. If we choose our axes so that they coincide with the principal axes of inertia, then we'll get that our kinetic energy T is equal to 1/2 m times v sub c x prime squared plus v sub c y prime squared plus v sub c z prime squared plus 1/2 times the quantity I sub x prime times omega sub x prime squared plus I sub y prime times omega sub y prime squared plus I sub z prime times omega sub z prime squared. All right, if the rigid body is constrained to rotate about some fixed point, then the kinetic energy reduces down to being equal to 1/2 omega sub p dotted with the angular momentum h sub p. So we lose all of the translational kinetic energy because it cannot translate. Okay. So potential energy corresponding to conservative forces and moments remain the same, but they're now 3D. The same is true for the work done by non-conservative forces. So we can just write then that the work done by some force W sub F is equal to the integral from position R1 to position R2, F dot dr. And then you can go and expand these like we did for gravity and springs or whatever you want. You can go and expand these as this integral as needed. And then for moments, we write W sub m is equal to the integral from some angular position theta sub 1, and that 2 some angular position, theta sub 2 of those moments dotted with dr, or d theta. And again, we can expand that as needed. And all of the things we found before, like for gravity, mgh, these are all true. You just now need to keep track of where it is in 3 dimensions, where the rigid body is in 3 dimensions, how its height's changing. Same thing with springs. Springs have the same force, same law, where it's 1/2 k times the deformation of the spring squared. That deformation now just depends on 3 directions. All right, we're now ready to move on to look at 3D motion, starting with the rate of change of angular momentum, and then we'll look at Euler's equations of motion. All right, we're going to consider a rigid body with a centroidal axis, capital X, Z, capital X prime, Y prime, Z prime, that have a fixed orientation in the frame, in some frame A, and then we have some body axis, lowercase x, y, z, that are fixed to the body, call that frame B. Those are rotating with that rigid body. So both of these axes are fixed, are attached to the center of mass. One of them, the ones in red, are rotating with the rigid body, or moving with that rigid body, rotating specifically. Both of them move with the rigid body, but the red ones, they rotate with the rigid body. The black x prime, y prime, z prime, those are attached to the center mass, move with the center mass, but they don't rotate ever. And then we have an inertial frame O with inertial axes x, y, z. This rigid body has an angular velocity of omega and some angular momentum h sub c relative to our frame A. Add a little e there. Okay, so h dot sub c, this represents the rate of change of h sub c with respect to those fixed orientation frame, or frame A. And it would seem natural to use the components of omega and omega sub c along those axes. However, since the body is rotating, our inertial tensor is going to change with respect to frame A here. It's going to change continuously in time, and we'll thus need to determine what those components are as functions of time. Instead of doing this, it's just more convenient to compute the time derivative using our body axes such that our inertial tensor stays the same throughout that motion. We're still going to define our angular velocity in the fixed frame that's attached at the center of mass, and then we'll project those onto the body axes. All right, we can then write that the rate of change of our angular momentum vector, h sub c, with respect to the rotating frame B is going to be, we'll write that this is derivative with respect to that body B, h sub c dot is equal to h dot c sub x in the I hat direction plus h cy dot in the j hat direction plus h sub cz dot in our k hat direction, where I, j, k are unit vectors along the rotating axis. And we simply just projected this angular rate of change of angular momentum onto that. We can then express the rate of angular change in the fixed frame as h sub c dot is equal to the derivative of h sub b, or h sub c dot in our frame B, plus we're going to get a capital omega crossed with h sub c, where We'll define each of these components. H sub c dot. This is the angular momentum of the body with respect to frame A with a fixed orientation. So frame A is not rotating. And H sub c dot with respect to B, this is the rate of change of H sub c, or the angular momentum, with respect to the rotating frame Our rotating frame is B. And then lastly, we have this capital omega. This is the angular velocity of our rotating frame. Given this, the governing equation of motion for the angular motion of the rigid body is going to be that the sum of the moments about the center of mass will be equal to the rate of change of our angular velocity, which will be h sub c dot computed with respect to frame B, plus omega crossed with h sub c. Okay, so when our rotating frame is attached to the body, which is what we've assumed up to now, then this capital omega is identically equal to what we use lowercase omega, or the angular velocity of the body. And in many applications, we will probably want to use a frame of reference that's not attached to the body, and then that frame then rotates in some independent way. In that case, this is where you end up with this capital omega. And just as an example, if the body's axisymmetric, then you can select a different reference frame where the inertial tensor is constant, but the frame actually rotates less than the body itself, which simplifies this analysis. All right, given that, we're now going to go into Euler's equations of motion, and then we'll end up going with taking a look at a gyroscope. All right, we're going to choose our body axes to correspond with the principal axes of inertia, and then our angular momentum will become h sub c is equal to I sub x omega x sub I plus I sub y omega sub y j plus I sub z times omega z k hat, and setting our capital omega equal to lowercase omega, our equations of motion are going to become that the sum of the moments in the x direction is going to be equal to Ix times omega x dot minus Iy minus Iz, that quantity times omega y times omega z. Then we'll get the sum of the moments in the y direction. It's equal to Iy omega y dot minus the quantity I sub z minus I sub x omega z. And then lastly, the sum of the moments omega z, or in the z direction, equal to I sub z omega z dot minus I sub x minus I sub y times omega y times omega x. And these equations are called Euler's equations of motion. So in general, the motion of a rigid body in 3D is going to be governed by 6 differential equations, 3 for translation and 3 for rotation. And just so you're aware, when we dealt with plane motion, Euler's equations still held. These were always still true there. We ended up just using the z equation. The other 2 equations represent constraint forces that force the body to stay in planar motion. So there are some moments that are acting on the body that force it to move only in a plane. All right, any questions so far? All right, then we will move on to looking at a gyroscope. So a gyroscope consists of some type of rotor that can spin freely. This guy right here, that is our rotor. It spins freely about its geometric axis. That's the axis C to C prime. It can assume any orientation, but its mass center is always going to remain fixed in space. In this case, they can measure and maintain orientations in space, and therefore they're a very key component used in navigation. As shown here, this rotor is connected to what are known as 2 gimbals. So the green and orange component, these are our gimbals, or the gimbals for this thing. This top image to the left, we're going to call that our reference position. So that is a 0, 0, 0 orientation. And now we're going to go through what we call Eulerian angles. And we're going to define the position of our gyroscope at any given time instant. We're going to select a fixed set of fixed frame with reference axes capital X, Y, Z, which is what was shown above and what is shown down here as well, although I guess the x-axis is now missing. We've chosen the reference position above. We're going to use that reference position to determine the orientation of our rigid body, or of the center of mass. We're going to do this to any arbitrary position using 3 steps, where the order of these steps is critical and matters. You cannot switch the order of these steps. We're going to start with a rotation of the outer gimbal. Through angle phi. Our second step, we are going to have a rotation of our inner gimbal through theta. So a rotation of the inner gimbal through theta. And then lastly, 3, we're going to have a rotation of the rotor through the angle psi. And just to repeat, you cannot switch the order of these rotations. If you switch the order, you will get a different orientation. So the order of rotation here matters, which is part of why orientation of a rigid body is a tricky thing to deal with, and part of why there isn't a generic or analytical formulation to go from angular velocity to orientation yet. All right, so the angles, phi, theta, and psi are called the Eulerian angles. They completely characterize the position of this gyroscope at any point in time. Their derivatives are phi dot, theta dot, and psi dot, define respectively the rate of precession, the rate of nutation, and the rate of spin. And just as a comment here, we've used these angles to define the orientation of a rigid body, of a gyroscope, but these are generic and can be used for any rigid body. It doesn't have to be a gyroscope. And these are very commonly used. All right. So we're going to now compute angular velocity and angular momentum of our gyroscope. To do this, we're going to select a rotating system of axes, lowercase x, y, z, attached to our inner gimbal, which is shown on the next page. And for a gyroscope, these are conveniently the axes of principal, or these axes are also the principal axes of inertia for this gyroscope. That is just a matter of convenience here. For a gyroscope, this is always true. For general rigid body, this is probably not true. It's part of what makes gyroscopes easier to deal with than just a generic rigid body. Okay, so we're going to denote unit vectors I, j, k along our rotating axis, and then we're going to need an additional unit vector k hat, capital K hat, along the fixed z axis. The diagram on the left has these in bolded vectors as bolded variables rather than hats. So then we're going to have here that omega will be equal to phi dot in our capital K hat direction plus theta dot in the j hat direction plus psi dot in the lowercase k hat direction. All right, so these three components are not on orthogonal directions, and as a result, we're going to project the capital K hat onto the rotating unit vectors. This will give us that capital K hat is equal to minus sine theta I hat plus cosine theta lowercase k hat, and then we can substitute that in for omega. We'll find that omega must be equal to minus phi dot sine theta I plus theta dot j plus the quantity psi dot plus phi dot cosine theta times lowercase k hat. All right, we're going to compute our angular momentum using the principal inertia tensor. And we'll write here that I, double underline, is equal to, for a disk, conveniently, we only end up with two inertias. We're going to get an I1, and an I2 down the diagonal. And then everywhere else is zeros. This is true because the body at the center of mast here, or at the center of the gyroscope, is a disk. If you have some other type of object there, then this won't be true. And then our angular momentum about point O, which is at the center of mass of this disk, H sub O is going to be equal to minus I1 v dot sine theta I plus I sub 1 theta dot in j hat direction plus I2 times quantity psi dot plus phi dot cosine theta k hat. And here we've assumed that our gimbals are massless, which in reality means their mass is so small we just neglect it. If we did not neglect them, then this becomes much more complicated, because we then have to account for their angular momentum as well. All right, we now need to compute the angular velocity of our rotating axes. They do not spin with psi dot, and as a result, our rotating axes are, or the angular velocity of them, capital omega, is equal to v dot capital K hat plus theta dot j hat, and that's then equal to minus psi dot sine theta I plus theta dot j plus phi dot cosine theta k hat. And with that, we're now ready to write out our equations of motion. You can write then that the sum of the moments about the point O is equal to H sub O dot computed with respect to B plus capital omega crossed with H sub O. If we write this out in components, we will get that the sum of the moments in the x direction is equal to minus I1 times phi double dot sine theta plus 2 theta dot phi dot cosine theta plus I2 times theta dot times the quantity psi dot plus phi dot cosine theta. So in our x direction, for the y direction, we'll get the sum of the moments in the y direction is then equal to I1 times the quantity theta double dot minus phi dot squared sine theta cosine theta plus I2 times phi dot sine theta times the quantity psi dot plus phi dot cosine theta. And then lastly, for the z direction, we'll get the sum of the moments in the z direction is equal to I2 times d over dt times psi dot plus phi dot cosine theta. And as I said before, these Eulerian angles can be used to define the orientation of any rigid body, not just a gyroscope.